Hey Fizz kids, Mr. C here, and today I'm going to talk about angular kinematics today. So sort of our next topic in rotational motion. So we're sort of moving away from torque, which is like the angular version of force, and we're moving toward angular kinematics, which is just how we measure motion in rotations. Like normal kinematics is how we measure translational motion, so whenever we're moving in straight lines. Angular kinematics is just how we measure motion whenever we're moving in a circle. And we're going to see actually as we go through this, it's pretty much it's run by the same principles that translational kinematics is run by. It's just we use different variables. So whenever we look at angular acceleration, like I said, we have to define a few new variables. So whenever we have translational motion, we use x for our position. Well, whenever we're talking about angular position, we're going to use theta. The same goes for displacement. We talk about delta x. Well, with angular motion, we're talking about delta theta, so our change in an angle. And we're going to talk more about position in a second. Now, for our velocity, instead of having a normal velocity, we have an angular velocity. And then for our acceleration, rather than having just a translational acceleration, we're going to have some alpha or an angular acceleration that has to do with how much we're speeding up while moving in a circle. We're going to talk about more about these as we get on in the slide. So that first one is angular position, and theta is just how we measure position whenever we're moving in a circle. And theta is measured from the positive x-axis. A positive theta we say is whenever it's going to be counterclockwise from the x-axis, and a negative theta is going to be clockwise from the x-axis. We measure theta in radians. I know some of you are going to be super excited about this because multiple of you guys have told me that, in calculus, they always say radians are superior. And, typically I agree with you, even though a lot of times we use degrees in physics. Well, whenever we're talking about angular motion, we're using radians, which is super cool. And then we also have this arc length, and the arc length, this S here that's in the picture, is actually the physical distance that the particle travels along its circular path. So like we moved through some theta radians as we moved, but we also moved some physical distance that we could measure out with a ruler. And that distance that we moved is S, or the arc length. And we know that even whenever we use a little bit of geometry, if you remember arc length from geometry, that the angle theta that we move is going to be equal to our arc length over s, or that arc length s is equal to r times theta. That's one equation you're definitely going to want to kind of keep in the back of your mind. Another useful conversion is that for a full circle, we know that the arc length over r is equal to 2 pi r over r, or just 2 pi radians. So one full circle, so one full revolution is going to be equal to 2 pi radians. And whenever we convert it, this is the useful part, is that we know that one revolution is going to be equal to 2 pi radians, which is equal to 360 degrees. And that's going to come in handy whenever we do things like whenever we're talking about something that's in rotations per minute, and we have to convert that into radians per second. We'll need to know how many radians are in one rotation. So the next thing we're going to talk about is this angular velocity, and the angular velocity is basically just the speed at which our angular displacement is changing in a sense. It's how fast we're moving around in a circle, and it's just going to be equal to delta theta over delta t. It's just how our normal velocity is delta x over delta t. In this case, it's just delta theta over delta t. It's how much angle we are covering every second, which is kind of cool. So like I see here, whenever we want to do dot diagrams, the closer your dots are together, the slower you're going. The further your dots are apart, the faster you're going. And whenever they're evenly spaced, we know that they were moving in uniform, constant angular motion. So the dot diagrams it runs by the same principles. It's just instead of moving some distance x every time, we're changing by the same angle. So I'm going to go ahead. So we know that we can relate angular and linear velocity. And the way that this sort of works is that we know that our angular speed, omega, is also going to be equal to 2 pi, which is one full revolution around a circle, divided by the time it takes to go around that circle. And we also know that every point on our object is rotating with the same omega. So it doesn't matter like what point A or B we're rotating at, but we're moving with the same angular velocity. However, we're not all moving with the same linear velocity. And we know that from back all the way in uniform circular motion, whenever we're rotating out, the further out you are, the faster you're going to be, you're moving, if you're moving with that same rotations, like if you're on a disk again. All the points move at the same angular velocity, but points closer to the disk have a smaller linear velocity. And the way that they're related is that our linear velocity is equal to our angular velocity times r. And like I said, the further out you get, the larger your velocity gets, and that makes sense. We'll talk more about this in class. So this is our first problem. I want you to go ahead and try this one out on your own and see if you can get the answer. But I want to know what the shaft's angular speed is. So go ahead and answer that in your notes packet, and then it's going to pop up on the on your question for your screen. But go ahead and answer that real quick before you move on. So our next one, the next variable is angular acceleration. And angular acceleration is the same thing as normal acceleration, except instead of your change in normal velocity over time, it's your change in angular velocity over time. And the units on that are going to be radians per second squared. So it's the same. Like I said, that normal acceleration is delta v over delta t. Well, angular acceleration is just delta omega over delta t. Whenever we look at signs, we say that alpha, that's what our angular acceleration, is going to be positive if we're speeding up in the counterclockwise direction, or we're rotating in the clockwise direction and slowing down. And we say alpha is negative whenever we're slowing down in the counterclockwise rotation, or if we're speeding up in the clockwise direction. So it kind of makes sense. It runs by the same rules as normal acceleration. We just have to take into account it's not really left and right is positive and negative, but rather counterclockwise is positive and clockwise is negative. So if you think back to the centripetal motion sort of unit, we know that objects moving in a circle will always have a centripetal acceleration. And whenever it's uniform circular motion in particular, we know that the speed is constant and the direction is changing, and that's why we have that acceleration that points toward the center, and we say that our uniform or centripetal acceleration is going to be equal to our velocity squared divided by r. And that's our linear velocity here, or translational velocity, divided by whatever our radius is. And that's all just sort of review from what we did last time. We also know that since our translational velocity is equal to omega r, we can rearrange this equation up here, and we can see that our centripetal acceleration is going to be equal to omega squared r. So it's just another way to write the exact same thing that we already know by plugging in this equation that we discovered a couple of slides. However, not all circular motion is going to be uniform. Sometimes we'll have a net torque acting on our system, and what happens then is we have some alpha. So our particle's actually accelerating as we're moving around the circle. So it's moving around the circle faster and faster and faster and faster and faster. And what happens here is we get a tangential acceleration, which is different than your centripetal acceleration. But the tangential acceleration is going to be the rate at which the particle speed changes around circle. So as we move around the circle faster and faster and faster, we have a tangential acceleration. A centripetal acceleration comes from the fact that our velocity is constantly changing direction. And we know that our our tangential acceleration is going to be equal to our angular acceleration times the radius that we're at. So once again, the closer into the circle you are, in this motion, the smaller your translational acceleration is going to be. The further away you are, the larger your translational acceleration is going to be. And whenever we're accelerating, as we can see in the picture here, while we're accelerating, our centripetal acceleration is constantly getting larger and larger and larger in magnitude, but our tangential acceleration is staying constant because alpha is not changing and r is not changing. But because our speed is changing, our centripetal acceleration is also going to be changing. Make sure you keep those two separate. One note on direction is your tangential acceleration is always going to be perpendicular to your centripetal acceleration. So centripetal acceleration points toward the center, and your tangential acceleration is going to point perpendicular to that. And you can have both of these at the same time. The biggest sort of example of this is when you increase the car speed while making a turn in the corner of a racetrack, or even as your tires are accelerating from rest. They're moving faster and faster and faster in a circle, and you're getting more and more forces acting on the particles in your tire. The tangential is due to changing speed, centripetal is due to changing direction. And finally, the last sort of thing that I'm going to end this video on is looking at the equations of motion, because we learned all about these translational equations of motion. Well, the rotational equations of motions have the exact same questions. Whenever we see any velocity in our translational motion, we just have to replace it with our angular velocity. And the same thing goes with, normal acceleration. We replace it with our angular acceleration. Or if we have our position, we replace it with our angular position or our radian. So it's the exact same equations. It's nothing new. They just have a different name to it, a different variable. So it's not like you have to relearn anything in this. They run by the same principles. They follow the same guidelines. They just have different shapes to their symbols. And we'll do some example problems with rotational kinematics whenever we get back in class. Sorry the video ran a little long. I was trying to keep it around 10 minutes, but that clearly did not happen. Make sure you answer all the questions in this video, and we'll talk more about rotational motion and rotational or angular kinematics, however you want to call it, in class when I see you next.